This course is presented by Systemverilog Academy, and please do subscribe our channel to watch more Systemverilog design, verification and UVM videos. Hello, welcome to this course, Systemverilog Verification, Learning More Testbench Constructs. Here is your chance to learn the complete Systemverilog course which are published in other paid platforms. This course is a continuation of the YouTube video titled Systemverilog Verification, Start Learning Testbench Constructs, which you can find the link in this I button. And if you are somebody new to Systemverilog, or if you don't know how to write a simple Systemverilog design and testbench program and how to simulate it, before going through this course, I would recommend you to first watch our Systemverilog videos titled Systemverilog for Absolute Beginners, the first program in Systemverilog, and also the video Systemverilog for Absolute Beginners, writing the testbench and simulating it for free. Once you have watched these videos, or if you are somebody comfortable in writing a simple Systemverilog design and testbench program and simulating it, you can start watching this course. These are the topics that is covered in this course, which are sequential and parallel blocks, fork joins, events, semaphores, cloaking blocks, interfaces, compiler directives, packages and parameters. And in this course you will be only going through the theory part of all these topics. Thank you for your interest in this course and happy learning. In this session you will be learning about sequential and parallel blocks. A block statement is a mean of grouping a number of statements together so that they looks correct syntactically to the language. So you know, a statement is an executable line which is ending with a semicolon. Most of the statements in Systemverilog will be ending with a semicolon. And if you wanted to group a number of statements together, that is what is called as a block statement. And there are two ways to do that. They are a sequential block or a parallel block. So the sequential block is also called a begin-end block, and a parallel block is also called as a fork join block. The reason is, a sequential block is written within a begin-end keyword and a parallel block is written within a fork join keyword. So in order to write a sequential block, you have to group a number of statements within a begin and end keyword. And the difference between these two are, in case of sequential statement, the statements will be executed in sequence, one after another of course, and the delay values in each statement will be computed in such a way that it is relative to the previous statement in that sequential block. And also the control will come out of this block only after the very last statement in this sequential block. In case of parallel blocks, which is put under a fork and join set of keywords, the statements within a parallel block will be executed concurrently or parallelly. And also remember that if there is a delay calculation in every statement or in any of the statement, all those delay calculations will be relative to the very beginning of the execution of the block. So there comes the big difference. In case of sequential block, the delay calculations were relative to the previous statement, but in case of a parallel block, it is relative to the starting point of execution of the parallel block. Also, the control will be coming out of this parallel block in three different ways, which we will learn in the coming session. So that is controlled by the behavior. That behavior is controlled by which join statement you are using, which you will see in short while. Now let's see an example. So here is a sequential block which is written in a begin and end set of keywords. You can see there are 4 statements and all of them are doing an assignment to the same variable named R. Just some different value hexadecimal 1, 1, 2, 2, 3, 3 and 4, 4, and say all of them are preceded with a #20 delay. Therefore, after every 20 time units, the variable R will be changing its value from 1, 1, 2, 2, 3, 3 and 4, 4. Oh, that is, in another word, it will be like in the simulation waveform. You will see at 20 time units the R will be equal to 1, 1, at 40 will be 2, 2, at 60 it will be 3, 3, and at 80 time units it will be equal to 4, 4. Now if you are writing the same set of statement in a parallel block which is again generating the same waveform, it will be looking like this. So it will be written in a fork join, but notice the difference in the time unit. So the first assignment is made after 20 time units, the second assignment is made after 40 units, third after 60, and the last one after 80 units. The reason is, in case of a parallel fork join block, all the statements, the execution of all statements within this fork join will be started immediately or at the very same point when the fork join is evaluated. So therefore, if you are writing the same set of statement here again within a parallel block, at the 20th time unit, all those values will be immediately changing. So in order to avoid that, you need to appropriately change the delay, keeping in mind that every statement is starting its execution at the same point in time. Also, since all of them are executing at the same point in time, there is no relevance for the order of the statements within the fork join. So this, if you're putting this very last statement at the very beginning, it will also produce the same waveforms as in the case of this previous example. In the previous lecture, you have learned about sequential and parallel blocks, and you will see more about fork joins in this lecture. So also remember that when you use a begin end block within a fork join, the entire block will be executed as a single process, and within that begin end, each statement will be executed sequentially. So what does it mean is, if you're just using a fork join with two simple statements, then statement 1 and statement 2 will start executing parallelly at the various point in time. But if you use a begin end block within fork join, then the whole set of statement which is blocked within a begin end will be treated as a one fork block. So this begin end block and this begin end block will be starting parallelly at the very same point in time, but within every begin end the statements will be evaluated sequentially. Here this begin end will be considered as a block and this begin end will be considered as a block, and both of them will be starting parallelly. Therefore, in effect, statement 1 and statement 3 will start at the very beginning of execution of this fork join. Now we will see more about the types of fork joins. So fork join can be of three types. In the join statement, you can use either a simple join or you can use a join any or a join none. The difference between these two comes in picture when the parent process, what happens to the fork join parent process at the end. So if I just using a simple join, then the parent process will be blocked until all the child process which are spanned are completed. But if you're using a fork join any, then the parent process will be blocked until any of this child process is getting completed. And in case of a fork join none, the parent process will not get blocked, or it will come out of this fork join immediately after launching all the child process threads. So we will see more examples of describing these three statements in the next slide. But before that, just understand that there are two more statements related to fork joins, which are disable and wait. So a disable fork will kill all the child process which are launched, and a wait fork will wait for all the child process which are launched. You're going to see all of them in details now. First, we will look at the simple fork join statement. So here is an example. Within a fork join, I have added three tasks named task A, task B, and task C. And after the fork join, another task is stated, which is task D. And here is a time axis. Assume that this is a the length of time that is taken by every task. So task A is completing in this much time. Task B is the longest task in this example, and task C is taking a time between A and B, and this is the time taken by task D. So this is the starting point of execution of this fork. The fork, and when fork is evaluated, all these three tasks, that is A, B, and C, will be launched or spanned immediately. So at this very point in time, all these tasks will be starting executing. And since it is a join statement, a join statement will wait for all the tasks which are launched. So here it will be waiting to reach this point, it will be waiting for all three tasks to be completed, which is only after the biggest or the longest task getting completed, which is a task B here. So this is the point in time when this join statement is completing. So And the next statement, which is the task D, will be launched or started only after this point in time. So only after completing all the child task or child process that is launched by the fork. Next is fork any, join any. So if you are using a fork join any instead of fork join, the difference is, instead of waiting for all the tasks to be completed by that is launched by the fork, the fork any will be waiting for any of the tasks that to get completed. That means the fork join any will be coming out of its execution when the smallest length task, the task which is taking the shortest time, is completing. So when in this example, when the task A is getting completed, it will be coming out of this point, and this is a point in time when this join any will be unblocked and going to the next statement, which is calling of task D. So when task D will be called immediately after task A is getting completed. So that is the difference between a fork and fork join any. Now quite often along with fork join any, you will see another construct named disable fork. So disable fork will be used to kill all the child process that is launched by the fork. So in this example, if you're using a disable fork after the join any, what will happen is it will kill all the remaining process when it is being executed. That means this point will be reached when task A is completed, and when disable fork is executed, it will kill all the threads that is being launched by this fork. So task A thread is already completed, therefore it will complete the task B and task C thread. Therefore what all statements were there in task B or task D till this point in time were executed, and if there are something remaining, they will not be executed. And after task A, task D will be starting its execution. So this is a use of disable fork. Next we will go to the final one, which is join none. So in case of a join none statement, all the threads will be launched within the fork statements, and it will not wait for any of the statements or any of the threads to be getting completed. So what does it mean is, so this is a starting point of this fork execution. So task A, task B and task C will be executed or evaluated or start executing, and immediately launching all these three threads, the execution will come out of this point, and it will not wait for anything, but it will go to the next statement. So therefore immediately after this, task D will be evaluated, or it will also get started. Therefore all these tasks A, B, C and D will get started eventually, and this is a difference between a fork and fork join none. Now assume that you wanted to make sure that all these tasks are getting executed, and you wanted to wait for something at this point. That means when all these tasks which are launched by this fork are being executed, you wanted to wait for that after some time. So then you can use the wait fork statement. So the wait fork will wait for all the tasks that is being launched within the fork statement. Therefore this will wait for the completion of task A, task B and task C. So by adding a wait fork statement, you can wait for this point in time in its execution. But note that it will not wait for the task D. It will be only waiting for the completion of all the tasks or all the threads that is being launched within this fork join or within the fork join statements. Thus a simple fork join will wait for all of its child process to get completed. A fork join any will wait for any of its child process to get completed, and fork join any could be used along with a disable fork. It's a good pair to use. And finally a fork join none will not wait for any of them to get completed, but it will immediately come out of the execution. And if you wanted to wait for its eventual execution, you can use a wait fork statement along with a fork join none statement. Welcome to the next video. In this lecture, you will learn more about interprocess communication. In the previous lecture, you have learned about fork join, and you have seen how you can launch different threads or different process or different tasks to execute parallelly or execute independently. In a real test bench, it is often necessary to communicate between these threads that is being launched from a higher hierarchy, or which are executing independently, which don't have any information about the other task or the parent task being executed. So interprocess communication and synchronization events are used to communicate between the process that is being launched independently or to synchronize between these processes. So these are the Systemverilog specific communication mechanism or synchronization and communication mechanisms available, which are semaphores, mailboxes, and named event. Out of these, semaphores and named events can be used to synchronize between different processes, and mailboxes can be used to communicate between different processes. You will learn more about these three in this lecture, and before that, just understand that both semaphore and mailbox are inbuilt class in Systemverilog, which is put in the STD's standard package. You don't necessarily need to consider them as classes. You can just consider them as some built-in data type, but effectively or actually they are some Systemverilog's built-in classes. First, we will look into semaphore. So semaphore is a resource management mechanism. So what does it mean is, if you have a set of resources which are limited and you wanted to share those resources across multiple processes or multiple clients, then you need to use a semaphore. As an example, imagine that you have a function or you have a task which is sending a set of transaction to a DUT interface, and since it is sending a transaction to the DUT interface, it can be called by only one client which is at a time, because it's a real-time interface communication, and the interface in the DUT is a single interface. So only one set of transaction can be sent at any point in time. And also assume that three different clients are sending transactions to this same DUT. Maybe it's three different classes, three different sequences, or three different agents, whatever it is. You need to limit the access of the actual task which is sending transaction between these three above upper layers. So in that case, you can use a semaphore. So here is the example, simple example. We will go back to the slide again, but just to make the point very clear. So these are the tasks, which is task A, task B, task C, maybe, which is being called by three different clients. And assume that there is a function to send a transaction into the DUT. So I haven't written that send a transaction task here, but this can be executed only by one client at a time to limit the access of the actual resource, which is in this case a function or task to send a transaction between three different clients or n set of consumers. You can use a semaphore. So here is a syntax to use a semaphore in Systemverilog: semaphore, then semaphore name. And in order to use a semaphore, after declaring, you need to first create the instance of the semaphore using a new function. After that, any client which is requesting that semaphore can get the semaphore by using the get function, and after consuming or after completing its consumption, it can return the key back to the resource manager by using the put method or the put function. So new, get, and put are the functions used along with semaphore to manage resources. And both get and put are blocking tasks. So the get task will get blocked until a semaphore key is available. So just to know if there is some key is available, if you wanted to make it as a non-blocking function, you can use try get function, which is a non-blocking in nature, which will just check whether something is available, and it will return a success value if something is available. And also note that along with all these set of methods, you can pass an optional argument, which is the number of keys. So when a semaphore is created using the new function, you can pass the number of keys to the semaphore. Say for example, if you're passing 1, so only a single key will be created and it need to be managed across different clients. But if you have, say, if you're creating with 3 keys, then at a time 3 different clients can get that semaphore. But if a 4th client is trying to get that semaphore again, it will be getting blocked. So that's the number of keys being generated. So the number of keys can be passed to all these methods as an argument, and if nothing is passed, the default argument value will be equal to 1. Now coming back to the same example, here in the module TB, I'm declaring a semaphore named Sema1, and in the initial begin or somewhere I'm creating that semaphore using a new function, which is, and also note that I'm passing a key at the number of keys as 1, and after that 3 tasks are being forked named A, B and C, and the task is actually, every task is getting the semaphore before doing the before actually sending the transaction. So sema1.get will get blocked until a semaphore key is available. In the same way, the same semaphore sema1.get in the task B will get blocked until the semaphore key is available. So based on what all are the functions or what all are the time consuming statements in this do something part, either task A or task B or task C will get the semaphore first, and then it will send the transaction, and then it will put back the key using the sema1.put function. Note that I am passing the number of keys as 1 for all these functions, all these methods. And once the semaphore key is put back by the task which is being consumed, which is consuming the semaphore, then some other task can get, some other semaphore get blocking call will be unblocked, and it will continue to the execution. And after that, don't forget to put back the key using the semaphore.put key. Now, if in case the semaphore.get calls in all the 3 tasks are being evaluated at the same point in time somehow, then any of them can randomly get the semaphore. It is not controlled by you. It is a random choice by the simulation. So any of these tasks can get, but you really don't need to worry about which one is getting, which task is getting the semaphore. Some task will get the semaphore, it will do the functionality and it will put it back. Then immediately in the same time region or in the same clock event, another task will get and it will execute the functionality and put it back. So you have seen about semaphores and their usages, and the important thing is always use the get and put in a pair in a set of process. So if somebody is taking the key, don't forget to put back the key after performing the required functionality. Now you will learn about Mailbox in Systemverilog. So Mailbox is a communication channel. So what does it mean is, it's a way to communicate between 2 different components which don't have any information each other. So it can be used to send a transaction from a generator to a consumer, or it can be sent to transaction between tasks as well. But most commonly it is used with pure Systemverilog based testbench, especially when they are class based testbench. And here is a syntax to declare a mailbox, then mailbox name, and these are the commonly used methods associated with mailbox, which are new, put and get. The new will create a mailbox and return a handle of it, and put and get methods are used to send something to the mailbox and get something from the mailbox. And also remember that by default the mailbox is typeless, so it can send any type of data in between. So we'll jump over to an example and see how a mailbox is used in a practical use case. So here is an example of using mailbox. These are written with classes. So the best way to demonstrate a mailbox is to explain how they can be used to communicate between classes. So if you are not familiar with Systemverilog classes, don't worry about the class part. Just go ahead and learn about mailbox. So in the first class, it's named AXA generator. A mailbox is a member in that. So I've declared a mailbox with name mbox within this class. And as you know, a class have a constructor with the name new. It's a must-have function within every classes in Systemverilog. So this is a function which is being called when the class is created. So the new function, within the new function, I am calling the new function of the mailbox again. So the mbox is created and returned to a handle. So mailbox is actually created within the class constructor function. And within the class, there is also another function named task. This is a user-defined name. You can give any name, but the new name you can't change. The function name, the constructor name must be equal to new. And here is a user-defined task. And in that, I'm just creating some transactions and sending the transactions. So this is a generated class. So again, AXITXN is another class which I have not shown here. So just understand that it's another class. It's a class which is representing a transaction. And in a for loop, the class is created 10 times. So this is how you create an object of a class in Systemverilog, and you are randomizing the class object. Again, if you're not familiar with the randomize function, don't worry about this, but just understand that once you call an object.randomize function of a random class, then it will generate random values to the member variable. So don't worry about it at all. So just understand that after this point, the transaction or individual transaction members have some values to send it. So now we are assigning values to this transaction. Then next job is to send this transaction to somebody, whoever is consuming it. So at this point, when this class is written, it doesn't know who is going to consume this transaction. So what it is doing is it is putting the transaction into this mailbox. Therefore, any consumer who is connected to this mailbox can take the transaction and consume it. So in the generated class, it is just putting the transaction into a mailbox now named mbox, which is a member variable of this class itself. Now coming to the driver part, the driver class is the one which is actually sending transaction to the DUT. So it need to have a virtual interface virtual interface handle, which is actual interface handle pointing to the DUT interface. Apart from this virtual interface, this driver class named AXI driver also contain a mailbox named mbox, and it is created using the new within this class constructor. Now the AXI driver also got another task named run, which is receiving transaction and sending this transaction into this interface. So in a repeated loop in a repeated for loop, so it is getting a transaction from this mailbox. So mbox.get will block until a transaction is seen in this mailbox, and after getting the transaction, it will be driven to this interface appropriately based on what kind of transaction and interface it is. So this whole loop is repeated for 10 times, and if you are using both of these classes together as a pair, this class will generate 10 transactions and put it into the mailbox, which is again a member variable within this class. And this AXI driver class is able to receive 10 transactions that is being if there are transactions available within this mailbox, and they will drive those transaction into the actual interface as well. Now, in order to use these two classes in the test bench, you need to create these classes and connect them appropriately. So that is done in this test bench module, where we are instantiating the interface and the DUT and the generator and the driver. And note that mgen is the generator name and mdriver is a driver name. And in the initial begin block, first a local mailbox is instantiated with name mbox1, and driver and generator is created using its new function. And the next step is you need to call the run task. So before calling the run task, you need to connect this driver and generator together, because this mailbox object within this class and this mailbox object within the driver class are both different objects, and you need to make a connection between them, or you need to make them as a same pointer. So that is done by this set of statements, which is mgen.mbox is equal to mbox1 and mdriver.mbox is equal to mbox1. Note that mbox1 is the local mailbox within this initial begin scope. Therefore, both this driver and generator is pointing to the same mailbox. So whenever its driver is sending a transaction to this its mbox mailbox, it will be available in the driver mailbox as well. And also you need to point the driver interface to this local interface instantiation as well. And I am forking this run task of driver and generator together so that they will start immediately. So whenever generator is sending a transaction, driver will be ready to get the transaction and it will be driven into the interface. And finally, when this 10 transactions are driven, I'm calling the $finish function. So this is the best example to demonstrate a usage of mailbox in Systemverilog. So this will be very much useful when you are using pure Systemverilog based classes. And so in order to connect between classes and send transactions through the classes, you need to use mailboxes. Now you will learn more about mailbox. So you have seen about mailbox, which is general in type. So just by declaring these mailboxes, even though we are sending only a specific type of transaction to this mailbox, you can put anything into this mailbox. You can put an integer, a string, whatever it is. So we are not restricting anything here. So in most of the circumstances, we wanted to restrict the mailbox to only to carry a specific data type. So that can be achieved by parameterizing the mailbox, and that can be done by passing a data type while you declare the mailbox. So this is a syntax to declare a mailbox with a parameterized data type, that is mailbox hash within the bracket the data type and m1. So the best usage of mailbox in the previous example should be like, when you declare the mailbox, it should be parameterized with the AXI transaction type. Note that AXI transaction is a type of transaction, or it's a type of class which is being generated and sent into this mailbox. So that in this example, the mailbox should be parameterized with the AXI TXN. So if you are trying to send another integer or string from here, it will flag an error here. In the same way, the driver mailbox will also should be parameterized with the AXI transaction. And also when you declare the initial mailbox or the local mailbox within its initial begin, which is used to connect this driver and generator, that again should be parameterized with this specific parameter, which is a specific class, which is AXI transaction. So in general, most probably you will always use mailbox as a parameterized type, which is used to send a specific type of transaction between different classes. These are the functions and tasks that comes along with the mailbox instantiations. The function new will return the mailbox handle, so it should be always created before using the mailbox. And you can optionally pass an argument to this new function. So if you are not passing anything, that mailbox will be unbounded. That means the mailbox size is infinite. You can send any number of transactions to the mailbox. But if you are passing an argument, an integer argument, a non-zero argument to this mailbox, then it represents the size of the mailbox queue. So if you're passing it as 100 at the time of creating the mailbox, only 100 transactions can be queued up in the mailbox. And after that, if you're trying to put some transaction into the mailbox, that put transaction will get blocked until one transaction is removed from its internal queue. Now we have already seen put transaction, so it stores that messages in the mailbox, and if it is a bounded one, it put will block if there is no enough space in the enough space in this queue. And in the same way, a get is again a blocking call, blocking task. It retrieves a transaction from the mailbox, and it also removes from the transaction that from the mailbox. And if the mailbox is empty, it will wait until it gets a message. So it's again a blocking task. So both put and get are blocking tasks. If there is no space to put will get blocked, and if nothing is there to get, the get will get blocked. Instead of these both put and get blocking tasks, you may optionally use the try put and try get blocking non-blocking functions. So this will return in 0 time. It will just check something is if we can put something into the mailbox, and if it can put, it will put, otherwise it will return immediately. It won't wait there to put it. In the same way, the try get will try to get a transaction from the mailbox, and if nothing is available, it will also get immediately. So these are just functions which are non-blocking in nature. Now another set of methods is peek and try peek. Peak is a tasks which is again similar to the get tasks. It's again blocking in nature, so it will wait until something is available in the mailbox, and if the mailbox is empty, it will block until something is coming into the mailbox. The difference between a peak and get is that a get will actually remove the object or the actual transaction from the mailbox, but what peak will do is it will just return a copy of the item that is present in that mailbox. It won't remove anything from the mailbox. So if you just keep on calling peak, nothing will get removed from the mailbox. And if you are specific about some scenario which you don't want to remove but you wanted to get something from the mailbox, you can use peak. And try peak is its non-blocking function version, so it will just try to peak. That means it will just try to get a copy of something. If something is available, it will return a copy of it. Otherwise, it will be returned immediately without blocking anything. And finally, there is also num method which will return the number of items or number of messages that is currently present in the mailbox. So it might be useful to check if the mailbox is empty at the end of your simulation sometimes. So you have learned about mailbox in detail. Mailboxes are quite commonly used in pure Systemverilog class-based testbench programming. But if your testbench is based on advanced Systemverilog methodology like UVM or OVM, you don't need to use mailbox directly in programming very oftenly, because they will have their own functions and tasks to communicate between different components. In the previous session, you have learned about semaphores and mailboxes, and finally you'll be learning about named event. So before looking into named event, let's see what's an event in Systemverilog. An event, in very simple words, is a change in the state of a variable. So Systemverilog language itself is more in the simulation. Systemverilog model will be advanced in its time as a set of, based on a set of event that is being executed. So whenever there is a change of state for a variable, that event is considered as an event, and that is again being called as an update event. And the evaluation of a variable itself is again named as an evaluation event. So in Systemverilog, the simulation time will be advanced in terms of updates events and evaluation events. So it's quite difficult to explain the concepts of Systemverilog simulation events in very few words, but you just understand at this point that a simulation in Systemverilog simulation, an event is a change in state of a variable. So all the events are implicit events, or in other words, the Systemverilog model itself is defined in terms of a set of discrete events. And apart from that, you are able to define another event, your own event, by using the event data type. So those events are named as named event, and you will be learning about named event in this session. So a named event is declared by using the event keyword, event even, and there are two actions with an event. An event can be triggered and you can wait for an event. So an event can be triggered by using this symbol in Systemverilog. So this is an example of triggering an event. And if you wanted to wait for the event to be triggered, you can wait for the event by using the @ symbol. So @ of event will wait for an event. So typically this can be used in a task which is spanned from the main task. So the main task could trigger the events at some logical point in simulation time, and another subtask or forked task can wait for this event to happen or event to get triggered. And this is how you use events or named events in Systemverilog, by declaring them, triggering them appropriately, and waiting for them in some other subtasks. Apart from this @ symbol, you can also wait for an event by using the triggered keyword, which is coming along with an event instance. So this is how you use a wait, or this is how you wait for an event using the triggered. So with wait, you will use the keyword wait, and within the bracket you will use the event.triggered. Both of these statements is in effect doing the same task, but this is a more recommended way of doing a wait for an event. And also, if you are interested in a sequence of event in a specific order, you can achieve by using the wait order function in Systemverilog. So in the wait order function, you can pass an event list. So for example, say if you're passing wait order A, B, C, where A, B, C should be of type this event, then this will suspend or this will wait until the current process is triggering events in the order like A, B, and C. And if they are not triggered in the same order, A followed by B followed by C, then the simulation error will be flagged. So that is the end of this session. In this session, you have learned in detail about semaphores, mailboxes, and events. So semaphores and events are quite often in testbench. Especially semaphores will be quite useful on all of the testbench, even if you are using a UVM based testbench. But a mailbox, it is used typically in a pure Systemverilog class-based testbench, and if your testbench is in a UVM-based or OVM-based testbench, you might not see a direct usage of mailbox in your testbench. Hello, welcome to the next session of this course, Systemverilog Verification, Learning More Testbench Constructs. In this session, you will be learning more about cloaking blocks. A cloaking block is a mechanism to synchronize the sampling and driving of input and output signals with respect to a clock event. So it will be quite useful to use cloaking blocks in a test bench to avoid race conditions in the simulation. So that assembles a cloaking block in Systemverilog assembles signals synchronous to a particular clock and makes their timing explicit. And before going into the details of implementation, we will just jump into an example and see how we can implement a cloaking block so that you will be more clear with the practical usage of the cloaking blocks. So this is a simplified syntax of cloaking blocks or defining a cloaking block. So you will use the keyword cloaking and encloaking, and you will use a name to identify this cloaking block. So in this example, you can give any name, and followed by at the rate symbol, you will give the cloaking event. And next, if you wanted to define default skew to this input and output arguments, you can define here with the default constructs. Otherwise, you can omit this and you can directly define the explicit signals cloaking skews like input skew and output skew. So let's see an example here. I have defined a cloaking block with name drv_cb. So it's a driver cloaking block. So it is sensitive to the positive edge of clock. So this is a synchronization event. The positive edge of this CLK signal is a synchronization event for this cloaking block. And in this example, instead of defining individual skews, I have defined the default skew for all the inputs and output here. So I am defining default input skew as input #1 step and output #0 step. So we will see what is the meaning of this #1 step and #0 in the next slide, but this is how you define a skew for the input and output variables. If you are not defining this default clocking skew here, you can explicitly define along with this input variable declaration and output variable declaration. It is possible to declare different skews for different input and output variables as well. And also remember that it is illegal to write any input clocking variable, and it is illegal to read from any output clocking variable. So what does it mean is, if you are using a signal with respect to a clocking block, that can be used, any input signal can only be used for reading and any output signal can only be used for driving. So you can use the signal within a clocking, you can access the signal within a clocking block with the name of the clocking block, it's dot signal name. So in this example, if you wanted to assign, say, AW valid as 1, you will be doing it like drv_cb dot AW valid equal to 1, something like that. Next, we will see how to specify clock skews. And here the skew means it's a skew in the simulation, and it is not the actual clock skew with respect to a hardware signal. So this is purely in terms of a simulation event. So the input skew is the time before the signal is sampled before the clocking event, and the output skew is the time after the clocking event when the signal is driven. So input skews are implicitly negative, that is, they are always referred to a time before the clock. So let's look at an example here. So if you're defining default input skew as input #5, It means the input values, whatever be the input values in this clocking block, when they are read, the value should be used at a point where which is 5 time step before the clocking event. So this will be a 5 time step. So time steps or time units is the basic time unit you can specify the simulation control. So if it is 1 nanosecond, so in this example it would be 5 nanosecond, where the value of this input signal will be the value of it before 5 nanosecond of this positive edge of this clock. And in the same way, default output skews are always referred a time which is after the clocking event. Therefore, so this is output skew. So if you're defining an output skew like #6, this will be after 6 time units after the positive edge of this clock. But quite often you will never specify this input and output skews with respect to a number, because you know this number is referring to an explicit time unit before and after, and if you're changing your clock period and clock frequency, so this might be, these values might also get changed. Therefore, in most of the cases, when you write very simple test benches, you might need to specify only 2 kind of skews. So in most of the cases, you will be specifying the input skew as #1 step and the output skew as #0. So note that it is not just #1, it is #1 step. So there is a special meaning for this #1 step with respect to, or in the context of an input skew in a clocking block. So a #1 step means it is a sampled value at the end of the previous time step postponed region, or it is a sampled value at the preponed region of this current clocking event. Therefore, it will be always a stable value which is derived after the previous clock. So, and in the same way, a explicit #0 delay, a #0 skew in the output means no skew at all. So it means all the driving of this variable will be taking place at the re-NBA region of this current time step. So if you are not very comfortable with the Systemverilog timing region at this point, you can ignore it, but just understand that if you're using a clocking block like this with the default or input #1 step and output #0, note that there is no steps after this output #0. It means you will always get a stable value of all the inputs from the previous time slot, and all outputs with a #0 delay, #0 skew will be driven at a stable point in the current time slot. Now, here are some more points about clocking blocks. So you can define a clocking block only inside a module, interface, or checker or program. So checker is an explicit Systemverilog keyword to abstract a number of assertions you can ignore at this point in time. And a program block is again a special kind of test bench construct where you can define your functionalities. So you will be allowed to define a clocking block only in any of these module, interface, checker, or program, but most commonly they are used and defined exclusively into an interface which will be widely used to drive signal from the test bench and to monitor signals from the DUT. And in the clocking block, if you wanted to wait for a clocking event within a clocking block, you can just specify the clocking block name and the clocking block name itself will serve as an event. So if you're defining as a clocking block like CB with name CB, which is sensitive to the positive edge of clock, and if you are wanted to wait for an event like at positive edge of clock, it will be equivalent to use just at CB. So you might see this at quite common in the test benches where clocking blocks is used. And 2 more points about clocking block is, if you wanted to define a default clocking block for all the signals in a specific hierarchy, say in an interface or in a module, somewhere like that, then you can add a default keyword before defining the clocking block. So that clocking block will be considered as the default clocking block until they are explicitly overridden somewhere else. So at this point, don't get confused about the default clocking skews. So in the previous slide, we have seen the default clocking skews for defining the default skews for input and output. So this is different. If you want me to make this clocking block itself as a default clocking block for every every variable in the scope, we can add it. And finally, it is also possible to define a global cloaking block which is applicable to the whole hierarchy by adding a global keyword before the cloaking block definition, and it is widely used in formal verification only. Just to summarize here, you will see cloaking blocks widely used in testbench, in quality testbenches, and they will be quite often defined in an interface, which you are going to see in the next lecture. And by default, in most of the cases, you will be defining the cloaking skews as input as hash 1 step and output as hash 0. Hello, welcome to the next session of this course, Systemverilog verification, learning more testbench constructs. In this video, you will be learning more about Systemverilog interfaces. The feature interface is something which is not present in Verilog language, but it is added to Systemverilog. So it's a widely used, a powerful feature for both design as well as verification code, and we will see how we can use Systemverilog interfaces for design and verification in this module. So interface is used to name a bundle of nets or wires together. So you can imagine an interface as something similar to a physical interface, which will have different sub signals or sub ports in it. So if you wanted to bundle them together, or all the signals together and access them together, you can use Systemverilog interface. So imagine you have a DUT which is dealing with AXI protocol. So these are the signals in a single AXI channel called AXI write address channel. So you can see that there are a lot of signals present here. Now if you're building a DUT or test bench which is using AXI interface, and there could be several sub modules in the design which is using this the same AXI signals, which wanted to propagate from the AXI signals from top till all the bottom units. So in all the places you wanted to explicitly write all these signals again and again wherever you wanted to specify these interfaces, these interface signals. So instead of that, what you can use is you can define a Systemverilog interface. So if you define a Systemverilog interface like this, instead of individually selecting all or listing all the signals in the module ports, you can give the name of the interface that you have written here as the module port. So we will see more about the usage in the coming sessions. Interface is a powerful mechanism which can be used widely across in these scenarios where you wanted to connect sub modules in the design or in the RTL code, or when you wanted to connect your design code and TB code together, or also if you wanted to reuse the TB components across different hierarchies like different submodules, clusters and top level unit. So we will straight away go to an example of writing an interface and using it in the test bench and the design code. But note that this is not the final code for using interface in test bench. We need to do some more addition to the interface and as well as to the test bench code, which we'll see in the coming sessions. So this is just a starting point. So the first block is defining an interface, which is naming as a simple interface, and it just got a clocking signal as input, and it got two logic members like request and grant. So these are the signals that is listed in the interface, and note that this is of type logic here. We are not specifying any directions here. It is not input here, it is not output here, it is just a logic direction here. It's just logic signal here. And in the design module or in the RTL module, you can pass this interface as an argument. Instead of individually passing the request and grant signal, you just need to pass the interface name here and its instance here. So this is of type, this INTF is of type symbol interface. So once you have passed your interface as a port list into the design or into a module, you can use it, access the individual signals of this interface with a dot operator. So it will be like intf.request equal to 1. You can assign intf.grant equal to 1 and something like that. So you will be accessing the individual signals within the interface using a dot operator. And now in the test bench, what you need to do is you need to define another instance of this interface which is local to this test bench. So you can see that symbol interface, its instance is defined like tb underscore with the name tb underscore indf. So it is very similar to instantiating a module. So you need to instantiate the interface as well. This design module is instantiated within the test bench like with the name design d1, and to its instantiation we are passing the interface instance as TB instance. So you can see that this is very much similar to you explicitly connect as a port signal. So in the same way you can explicitly connect an interface as well, but these should be of the same type here. So after creating an instance of the interface within the test bench and connecting it to the DUT, what you need to do is you need to drive signals into this local instance of the interface. So it can be done something similar to here in any procedural block. At positive edge of this interface dot clock signal, you can drive signal like tb dot request is assigned with value 1 using a non-blocking assignment. So this is how you can define interface and use them in design and TB module. If you wanted to access the individual signals of interface, you need to use the dot operator. So you have seen a simplest example of defining an interface and using them in a design and test bench. But in the coming session, you will be learning more about interfaces, and finally you'll be able to write a complex interface. Not a complex interface, a complete interface which can be modeled, which can be reused across design and test bench and across hierarchies. In the last video, you have seen how to define an interface and use them in design and test bench. But in that example, you were declaring all the signals as a simple logic type. You are not specifying or insisting the type of the signal, whether it is an input or an output. But you can just leave the signals like in a design module. Especially in the design, if in the RTL module, you need to specify whether it is a input direction, input port, or an output port. So in order to facilitate that, Systemverilog support one more additional type specification within interface, which is called modport. So modport is a way of specifying the direction of signals which are local to the interface. So you can define multiple modports in the same interface. So in every modport, the directions of the same signal can be different. So the typical usage example is master-slave communication. So if you are considering an AXI protocol, it got a master and slave drivers. So if master is driving the signals, then slave is accepting the signal. So in the AXI interface, all the signals, ID, address, length, size, burst, etc. are driven from the master along with the valid signal. And whenever these signals are accepted by the slave, or whenever the slave is ready to accept the signal, the slave will drive the ready signal. So when this interface is used in a master device or master design, all the signals right from here AWID to AWValid are outputs and AWReady is an input. So that is specified by using a modport like this, modport. So modport is a keyword here, modport. So this is a user defined name. You can give any name here. Here I have given a master. And within the bracket, you can specify the direction of these signals in this modport. So in the master modport, all the signals are output and AWReady is input. And in the other way, I have defined one more modport named slave. And in the slave modport, all the signals are inputs and ready is an output. Now we will see how these modports can be used in the design module. So it's the same interface with name AXI write address INTF, and it got two modports, name master and slave, which you had seen in the previous slide. So just here the master and slave modports are named, highlighted with a different color just for easiness. And when you use this modport in a design, assume in this case your design is a master design. So you wanted to use the modport, the master modport, or you wanted to use this interface in the master direction where all the signals are outputs and this ready is an input. So in that case, in the port list, in the design or the RTL port list, you will define the interface.modport. So AXI write ADDR INDF dot master, and then you will specify the local instance name, the interface instance name. So this, in this example, this INTF is an interface type, and all the signals within this interface got this master mode port direction. Or in other words, this is exactly same as defining all these signals as output and the signal as input here. And again, after defining this in the module port list, you can use them with this local instance name. We can access individual signals like INTF.request and so on. Now we have seen about using modports in design. Now let's see what about a test bench. So shall we use this simple modports in the test bench as well? So the answer will be no. So in the test bench, instead of modport, you need to use cloaking blocks to get predictable simulation behavior. You have already learned about cloaking blocks in the previous session, and also you'll be learning how to define cloaking block and use them in the interface in the next slide. But before that, let us ask a question. How do we define an interface, a generalized interface, which can be used in both design and test bench? Or in other words, how do we define an interface which is a common file which can be used for both design and test bench? So the problem is in the design, you will have say both master and slave modes, and you need to access the individual signals in different modules. And in the TB, you need 3 different modes: a master mode, slave mode, and a monitor mode. So to make it clear, so assume this is your top RTL design block diagram. It got 2 AXI devices or AXI submodules. One is an AXI master, and another one is an AXI slave. So this will be a module. This will be again another module, and you need to connect these two together using AXI interfaces here. So what you need to do is you need to define an AXI interface, a Systemverilog interface with some name, which can be used in this module and in this module, and also in the top design module. And the same file need to be used in the test bench as well. And in the test bench, there are 3 components or 3 different modes of test bench. In the first mode, you will be testing the AXI slave unit with a test bench which is working in the master mode, and in the second mode you will be testing this AXI master subunit with the test bench which is acting as a AXI slave, and finally in the third mode you will be testing the whole design or the whole top design, and in that case your test bench will be sitting outside, and you need to drive this top levels design signals appropriately. So next slide shows his definition of such an interface, which can be used across different design files and across different test benches as well. So the interface name is AXI write ADDR interface, and after all the logic signals need to be defined like this. And after that, it got 2 mode ports named master and slave. So it is exactly the same that you have seen in the previous slide. The master and slave will define the direction of this output and input appropriately. So in the design, when it is design is using as a master device, it will be instantiating the interface dot master, and in the slave design subunit, it will be instantiating like interface dot slave mode port. And apart from that, to use this interface in the test bench, you need to define appropriate cloaking blocks. So in this case, you need 3 different cloaking blocks. You need a cloaking block where you want to drive signals in the master mode. So I am naming that cloaking block as DRV underscore and MS underscore CB. And all these cloaking blocks uses the default input as hash 1 step and output as hash 0, which you have learned in the previous session. And the drive master cloaking block is defining all the signals as output, and this is input. And in the same way, one more cloaking block is defined with name drive slave cloaking block, where all the signals as input and this signal is an output. And apart from these 2 cloaking blocks, we need to define one more cloaking block which can be used to monitor this interface in the top level. So when when you are instantiating the whole hierarchy and you are using this in the top level test bench, you might want to monitor these signals. This interface is not driving anything. It's not driving any master or even the slave signals, because the modules within this design, or the design itself, will drive signals in this interface. So there is nothing to drive from this top level test bench into this AX interface, but the design need to monitor, need to snoop this interface and see what is happening in this interface, so that it can check different transactions. So for that mode, you need to define a monitor clocking block, and in that monitor clocking block, all your signals will be defined as an input directions. And this is a common structure of defining interface. The interface may or may not have mode ports. If the interface is not used in the design files, you don't need to define mode ports. But if you're using this interface in the test bench, you need to define clocking blocks within this interface, and different clocking blocks will define different direction of inputs and outputs. And also you will be defining a monitor clocking block, which is used to monitor or snoop all these signals, which is driving nothing, but which is always monitoring. And after defining this interface in the same way, you can use it in both design and test bench file. So in the design, so we have seen in the previous slide, it will be it will be in the port list, it will be used like the interface.mode port, then this local interface instance name. So in this example, say assume the design is a slave design and the test bench is a master test bench, and the design module uses interface.slave mode port here, and you can access the individual signals like indf individual signals. And in the test bench, you will instantiate the simple interface with some name, and you will pass it into the design. And when you drive signals into this design, you will be using the drive master clocking block. So say if you wanted to wait for a clocking event, you will be using at a tb interface dot this particular clocking block, drive master clocking block. And also if you wanted to drive signals into this interface, you will be using like in the tb interface dot this drive master clocking block dot request is equal to some value, and it should be assigned with a NB assignment or non-blocking assignment. So this is a generalized way of defining interface and using it in design and test bench. To summarize, you will define interface. You need to define mode ports in the interface if this interface is used in the design, and you need to define appropriate clocking blocks in the interface to use them in different test bench hierarchies. And when you drive signals from this test bench, you need to use the appropriate clocking blocks dot signal name in the interface. Remember this is a generalized way. This is true for even in case of a UVM based test bench. Even if you are writing your components in UVM, the interface in a UVM based test bench will look exactly similar to this. It will have a master clocking block, a slave clocking block, and a monitor clocking block. Compiler directives in Systemverilog. Compiler directive in any programming language is a way to pass instruction to the compiler so that you can make your code more reusable across different hierarchies and different files. Here is a list of all compiler directives in Systemverilog, out of which the ones which are listed in the left hand side are quite commonly used across different test benches, and the one in the right hand side are not commonly used. I am not going to explain these here, but we'll quickly see what are the use cases of these compiler directives. So the first one is tick include. It is used to include a file into a different file. So the general format would be either tick include within double quotes you can give the file name, or within these set of symbols you can give the file name. And the next one would be tick define. So if you are familiar with the tick define functionalities in C, this is similar to that. You can define any set of functionality using tick define, and the compiler will just replace that definition with its original definition whenever it is encountered. So for example, if you're defining a text like tick define, so this will be the macro here. DSP is the macro. You can optionally give arguments to the macro. If you wanted to give argument, you need to use a set of brackets here, and if there is no bracket, it won't take any argument. So in this case, this is taking two arguments. This macro DSP is taking two arguments, X and Y, and this macro is saying initial $display start X, Y, N. So what happens is after defining this macro DSP, if you use including this macro tick DSP somewhere in your code with set of arguments, say for example hello and world, those are the arguments passed to this macro, then when the compiler is expanding this macro, it will be equivalent to writing this set of code with replacing these X and Y values with these two values. So it will be equivalent to writing initial $display start hello world end. So it will be exactly equal to, the compiler will replace this macro with this set of line of code. So this is a use case of tick define. So another use case would be if you're defining, say, a word size as 8 using tick define, you can use that word size in even in the size specification parameter in an array like tick logic tick word size minus 1 down to 0 data, so which will be equivalent to 8 minus 1 down to 0, so it will be equivalent to 7 down to 0 of data. So after defining a lot of macros, if you wanted to undefine them, or if you wanted to remove the definition, you can use a tick undef all macro, which will undefine all the macros which I have already encountered with this tick define. And the next set of compiler directives will be tick ifdef, tick else, if, endif, and tick endif. So these are again conditional compilation macros, which might be quite useful, especially if you're sharing files across different units and so on. So we'll see an example. So assume that you have a common file which is used across, say, two different units, TB unit A and TB unit B, and all your file parts is exactly same, but only a single line is changing across unit A and unit B. So in unit A, you wanted to drive an interface signal with, say, some value AA, and in unit B, say, you wanted to drive the same signal with value B. And there will be a lot of code in this file, and you don't want to replicate this file into two different units. So in that case, you can use a tick ifdef compiler directive. So you can say tick ifdef TB unit A, then this will be your ID value. Otherwise, this will be your ID value. So it doesn't have any significance to what is written over here. So it is just equivalent to, if this macro is defined, then it will compile all these things, and if it is not defined, it will compile all those things. So even if you are making a compilation error, a syntactical error in this part, and if you are defining this TB unit A using a tick define, then it won't be cached in the compilation. So tick define, along with the tick define, you can use the tick ifdef, tick else, tick endif, all those macros to selectively compile a set of code in a file. So after defining this ifdef and tick else part, you need to define tick define TB unit A in the unit A file, so that it will be included. The compilation will be seeing this part of the code. And in the TB unit B, you should not define this macro, or you should, if it is already defined, you should undef this macro. Next one is timescale. So the timescale unit is the timescale macro is used to specify the time unit and time precision in the current simulation. Time unit is a time of a single step in the simulation. So a single time step is a time unit, and time precision is the precision value to which is every time unit need to be rounded if there is a fraction time. So we'll see an example. Assume we are defining a time scale macro with time unit as 10 nanosecond and time precision as 1 nanosecond. So it means the time values are multiples of 10 nanosecond, and every time unit, if it's a fractional time unit, will be rounded to the nearest 1 nanosecond. So let's see an example. If say in the test bench, in an always block, if you are changing the clock value after every 50 time units, so in the simulation you will see that every time unit is 10 nanoseconds. Therefore, after every 50 into 10 equal to 500 nanoseconds, the clock value will be changing, or it will be toggling from 0 to 1, 0 and 1, and your clock period will be 500 plus 500 equal to 1000 nanoseconds. And the time precision comes to picture when there is a fraction in the time unit. So for example, say consider this statement: initial begin hash 1.55 a is equal to 0. So after 1.55 time units, a need to be assigned to 0. So to find the value of the 1.55, this will be multiplied with the time unit first. So it will be equal to 15.5 time units. So as you know, the time precision is 1 nanosecond, so therefore it will be adjusted to the nearest 1 nanosecond, which will be equal to 16 nanosecond. Therefore this statement means after 16 nanosecond a will be equal to 0, and again after 16 nanosecond a will be equal to 1, with the time unit of 10 nanosecond and times precision of 1 nanosecond. Packages in Systemverilog. Package is a powerful Systemverilog specific features which helps to share common defines and common code across different files and different hierarchies. So they are explicitly named scopes appearing at the topmost level of the source text, and within a package you can define any types, parameters, nets, variable, functions, tasks, sequences, properties, etc. And you can use those packages in any of those modules, interfaces, programs, and some other packages, etc. So a package will be defined within a package and end package keyword, and we'll see an example in this slide. So here I'm defining a package named my package. So it is defined within the package and end package keyword, and it is defining two type definitions for enumeration, like with the name bool underscore t and axa resp underscore t. And in order to use these typed of enumerations in some other components, say in a module, you need to import this package into this module scope. So that can be done in two different ways. Either you can refer those package explicitly using the package scope resolution operator, which is : So if you wanted to refer this bool t in some other modules, you can refer like my package : bool t, then declare a variable of the type b1 and assign it with the value false, which is again defined within this my package. Therefore you need to again use my package : false. And the second method is importing the package. So by using the import keyword, you can import this package into another file or another package or another module. So here is an example. Within the module mod1, I have imported this my pkg, and here I have used a star import. So if you wanted to import everything in one package to another place, you can just use a star keyword. So the package name : the star keyword, which will import everything that is defined in this package into the scope, and after that you are free to use whatever is defined within this package as if like it is already defined within this scope. So for you can declare variable of axa response type, say a1 is equal to OK, you can assign a value, and also you can declare this bool type variable and assign a value. And if you don't want to import everything, but if you are very specific to importing a particular sub part of this package, that is also possible. So instead of that star, you just import whatever you need to import. So import my package : axrst. So in this module 2, only this item with axa response t enumeration will be imported, and therefore you are free to define a variable of this type. But since it is not importing everything, or it is not explicitly importing this bool t as well, you can't define a variable of bool t type within module 2. This is a very simplified explanation of using packages in Systemverilog. So you can define different packages and you can import one package from another package, and also it's allowed to define the same items in multiple packages and import them appropriately. So there are many combinations possible. Some are legal, some are illegal, but most commonly everything that is common across different files will be defined in a package, and the people who are using those common items will be importing those packages. So even if you're using a UVM test bench, the whole UVM methodology itself will be available within a package called UVM_pkg. In the same way, you can define your own test bench packages, your own general definition packages, etc., and import appropriately. So before binding up, just understand that there is a built-in package in Systemverilog which is named as STD. So the STD package in Systemverilog provides a lot of built-in code that is ready to use into your code. Some of them are the Semaphore class, the Mailbox class, the randomize function, the process class, etc. So while learning Semaphore, you have learned that Semaphore is a built-in class, and that class is defined in the standard STD package. And this STD package will be implicitly a wildcard imported into this compilation scope. So you don't need to explicitly specify like import STD. It will be implicitly available in the compilation scope. Constants and parameters in Systemverilog. In this session, you will quickly go through Systemverilog, constants and parameter, how to define a parameter or constant in a module or in a package and use them. So there are two types of constants in Systemverilog, which are elaboration time constants and runtime constants. So elaboration time constant will be selecting or fixing their value during compilation and elaboration, and the runtime constants will be selecting their value when the test actually simulates or simulation runs. So elaboration time constants are parameters, local param, spec param and def param, and the runtime constant is the const keyword. So out of which spec param is specifically used in the specify block, which is out of the scope of this course, and again def param is not recommended to use, and the remaining two elaboration time constants are parameter and local parameter. So in Systemverilog there is no much difference between the terms parameter and local param, but in Verilog both parameters and local param were totally different, but when coming into Systemverilog both of them are almost identical. You can use them interchangeably. And if you consider parameter or local parameter, again there are two types of parameters, which is a value parameter and a type parameter. So we will see how to define a value parameter and type parameter in the next slide and how to use them. A parameter can be defined using the parameter keyword followed by the parameter constant. So instead of this parameter keyword, if you use this local param keyword, as I said earlier, in Systemverilog the effect will be almost same. And you can have the parameter constant in two different ways. Either you can have the type and range specification, or you can skip that. So if you want your parameter to be always a logic 7 down to 0 type, you can define like parameter logic 7 down to 0. Then this is the name of the parameter, and this will be the value of the parameter. So whenever the code encounters width, the name width after this, it will always replace with a logic 7 down to 0 16 value constant. And if you are not giving this type of this parameter, by default it will be integer. You can again straight away give the parameter value like parameter width is equal to 16. So this is called value parameter, where you will define a value, or where you will specify the parameter with a value. In Systemverilog, it's also possible to define type parameter. So type parameter is where when you define a module or a class or an interface, where you don't want to specify or insist the type of an argument that is being passed. So we will see an example here. Here I have declared a module named FIFO, and it is parameterized. So a module or a class is parameterized by using the hash symbol. So while declaring the module or interface or the class, after the hash symbol within the bracket list down all the parameters. So that is the generalized way to define a module or interface or a class as parameterized. and you can list all the parameters, any number of parameters you can give, and also you can give the default value for these parameters with an equal to symbol. So within the module there will be a parameter defined width which will be equal to 32, and there will be another parameter called my type, and you can see that in the second case this parameter is a type parameter. So a parameter is made as a type parameter by appending the keyword type. So when you define parameter type, that parameter will become a type parameter, and the advantage would be you can pass any valid data type to this my type here. So by the default type would be equal to integer. So if you are not insisting anything here, the my type would be integer. So once you declared a type parameter like that, you can use from this point, you can use anywhere in this module or class. So you can see that in the port list itself I have used. So in the input, instead of saying int a comma b, or say logic 7 down to 0 a comma b, I have just put my type a comma b. So this is completely compile compatible, because this my type is a local parameter which is again a type parameter here, and you also for type parameters you should give a default value for all the type parameters. Now after defining a type parameter like this, when you instantiate this module, you can change the parameter type. So you can change the input port type to anything that you want. You can make instantiate this FIFO with the second parameter as logic 7 down to 0, or a byte, or a bit, or an integer, or a real, whatever it is. So that just by changing the parameter at the instance, you can simply change the port type that is defined within this module. Parameter is a very powerful mechanism to make your code more reusable across different hierarchies and different projects. You will quite often see parameterized modules, parameterized classes in design and test bench code. Also, parameters are quite commonly defined in a package. So when you define a parameter in a package, it will just serve as a constant which will be defined in a single place and used in multiple places. So you have learned about parameters and their definition and usage. So remember that parameters are elaboration time constants which are getting fixed their value during compilation, and the key, when you use the keyword const, it will be a runtime constant and its value will be fixed during simulation. So typical usage of a constant would be to access a hierarchy in a module. So the hierarchy will be fixed only after compilation. So if you wanted to access some fixed hierarchy, you have to use a const keyword and access it through a constant. Hello and welcome to the very last session of this course, Systemverilog Verification, Learning More Test Bench Constructs. So in this course, you have learned about sequential and parallel blocks. Also, you have learned about different types of fork joins. And next we learned about semaphores, events and mailboxes. Also, you have learned about clocking blocks, interfaces, modports, and how to use clocking block within interfaces. And then you again gone through compiler directives, and you also seen some example of using some useful compiler directives. And finally, you have learned about packages and parameters. So this was a basic level course in Systemverilog, and the topics which are not covered in this course are the topics which I have already covered in this first series of this course, titled Systemverilog Verification 1, Start Learning Test Bench Constructs. And this course is a continuation of this previous course. And also, along with these two courses, I haven't covered anything about classes, random constructs, assertions, and functional coverage, as each of them are very wide topics which need to be explicitly covered. So I have covered each of them in different courses. Congratulations, finally you have reached the end of this course and you have successfully completed this course. Thank you very much for enrolling this course. I hope this course was relevant for you and you have learned a lot from this course. I would really appreciate if you could leave your honest feedback about this course. Thank you again and happy learning. This is presented by Systemverilog Academy, and if you like the video, please do subscribe our channel for more Systemverilog design, verification and UVM videos. Also, don't forget to take a look at the different playlists that we have created in our channel, which will teach a set of selected topics in Systemverilog. Thank you for watching.